Okay, we'll get a start into the next section here. So actually the next three sections are all very related. 4.3, 4.4, and 4.5 is all about logarithmic functions. So I'm going to give you, kind of the information with those sections together, although there's a topic that we'll wait and do afterwards though. It says that an exponential function, y equals a to the x, that's what we just talked about, is a one-to-one function. Okay, so remember one-to-one means that the inverse is a function. Okay, now inverse is all about switching x and y. So if I switch x and y in this equation, I have the equation x equals a to the y. Now that inverse, x equals a to the y, is so important in math that we give it a special name. We call it the logarithmic function. Okay, I'm going to give you now a formal definition of that. So a definition, it says that the logarithmic function to the base a, where a is a positive number and a can't be 1, is denoted by y equals log base a of x. And it is defined by y equals log base a of x if and only if x equals a to the y. So this equation here happens. Okay, a couple things. First of all, the logarithmic function is like any other function. There's input values and output values, right? The x values are the input values. The y values are the output values. A is the base. A has to be a positive number, but a can't be 1. Okay? Now the phrase if and only if is a phrase that sometimes comes about in various math classes, and all we mean by that is that there's two if-then statements going on. So one way that you can read this line here would be to say if y equals log base a of x, then x equals a to the y, right? Like, so read it normally, beginning to end. Another way that I could read it though, and have it still be true, is to read it end to beginning. Okay, I could say if x equals a to the y, then y equals log base a of x. Okay, that means the same thing. So that's basically what the phrase if and only if means. Okay. Now I would memorize this definition because so much of what we do with logarithms revolves around this one statement here. And if you don't know the definition of a logarithm, that's going to be a huge problem in these three sections, okay? And on the test, okay? So definitely make sure that you know this definition here. That's probably the most important thing in all of chapter 4, okay? Now as a note, the domain of any logarithmic function is all positive numbers. Okay, so I can't take log of 0, and I can't take log of a negative. Okay, let's take a look at an example. So now the base also has to be a positive number. So what if I let the base be 2? I want us to graph y equals log base 2 of x. Okay, well, if I switch that over to an exponential form, using this definition, x equals a to the y, a is 2, I have the equation x equals 2 to the y. Okay, and let me assign specific numbers here to this. If I let y be 3 and x be 8, then I have the equation 3 equals log base 2 of 8. Okay, what that means, x equals a to the y, the x value is 8, a is 2, and y is 3. Okay, so I have the equation 8 equals 2 to the third power. Right, and that'd be a true statement, right? 2 cubed is 8. It's just another way to say that 2 cubed is 8 is to use this logarithmic form. 3 equals log base 2 of 8, that means exactly the same thing. Okay? So now the next thing that I want us to do is I want us to get a graph of y equals log base 2 of x. Before we do that, I'm going to have us first regraph y equals 2 to the x, because y equals 2 to the x is going to play a role in how I get the graph of y equals log base 2 of x. Okay? So y equals 2 to the x, we've already graphed that in the last two sections, in 4.1 and 4.2. I'm just going to use the same list of numbers that I had used previously in that table. Okay? So like if I let x be negative 3, 2 to the negative third power, that's the same as 1 over 2 cubed, or 1/8. Okay, so negative 3 1/8, that point would be on the graph there. If I let x be negative 2, I have 2 to the negative second power, that's the same as 1/4. So negative 2 1/4, that point is on the graph. If I let x be negative 1, 2 to the negative first power is 1/2. So there'd be the point negative 1 1/2 on the graph. If I let x be 1, anything to the 0 power is always 1, right? So this curve, just like any other basic exponential, y equals a to the x is always going to cross through the y-axis at 0, 1. Okay, so here's 0, 1. If I let x be 1, 2 to the first is 2, so 1, 2, that point is on the graph. If x is 2, 2 squared is 4. Okay, so there's 2, 4 on the graph. And then if we let x be 3, 2 cubed is 8. Okay, so that point is on the graph, 3, 8. Okay, and after I got these points plotted, I can draw the curve. It's going to be it's going to be starting off in quadrant 2, and we'll slightly head upward, and we'll cross the y-axis at 0, 1. And if we cross at that spot, we're going to shoot upward and outward into quadrant 1. Okay, there's a horizontal asymptote on the graph of an exponential. Okay, so right here, y equals 0. No matter what I let x be, x can be positive or negative or 0. I'll never have a negative coming out of this. I'll also never have 0 coming out of this. Okay, so this curve is going to get closer and closer to y equals 0, but it's never going to get there. Okay, so that's the graph of y equals 2 to the x, and we have been there and done that before. Okay, so I'm not showing you anything new with that. Now, the first thing that I said in this section is that an exponential function y equals a to the x is a one-to-one function. What does that mean? It means that the inverse is a function. Okay, there's the word inverse. Well, inverse is all about switching x and y. So with this equation, y equals 2 to the x, all I'm going to do is switch x and y. And I have the equation x equals 2 to the y. X equals 2 to the y means y equals log base 2 of x, right? Here's if and only if. So I can read this beginning to end or end to beginning. They mean the same thing. So x equals 2 to the y, that means y equals log base 2 of x. So if I want to graph y equals log base 2 of x, I need to graph the inverse function of y equals 2 to the x. Okay, well, there I go saying the word inverse again. All I'm going to do is I'm going to switch these x and y values on these points that I've got plotted. Okay, so let's do that. Negative 3 1/8, that's going to be at 1/8 negative 3, right there. Negative 2 1/4, that would be at the point 1/4 negative 2. Okay. Negative 1 1/2, that's going to be at the point 1/2 negative 1. 0 1 would be at 1 0. 1 2 would be at 2 1. 2 4 would be at 4 2. And 3 8 is going to be at 8 3. Okay, so then after I got those points plotted, I'll go ahead and draw the curve. Now, all the points are just getting flipped, the x and y values. Okay, that includes the asymptote. So we had a horizontal asymptote on this exponential function. That's going to turn into a vertical asymptote on the graph of the logarithm. Now, that's a feature of drawing a logarithmic curve, is that there will always be a vertical asymptote on the graph of a logarithm, okay, because you're just switching the coordinates there from an exponential, okay? Now, let's go ahead and graph the line y equals x. Okay, y equals x, that's the diagonal line in quadrants 1 and 3. So what I'm saying is that one way to get the graph of y equals log base 2 of x is all we did was we rotated the curve y equals 2 to the x about that diagonal line, right? Because these two curves are symmetric about the diagonal line. That will always happen. That will always happen. So whenever you graph an exponential and its inverse, which is a logarithm, side by side or on the same picture, they will always be symmetric to the diagonal line y equals x. Okay? And that's how I have to graph a logarithm. Okay? I need to first start off by graphing the corresponding exponential, and then I switch all the coordinates. Okay? So if I wanted to graph y equals log base 5 of x, I would have to first graph y equals 5 to the x, and then I switch all the coordinates, and then I get the graph of y equals log base 5 of x. Okay. Now let me go back to this statement here, this definition. Y equals log base a of x means x equals a to the y. Okay. So that's very important. I would say put a star by that statement. Definitely make sure you know that. Okay. We need to get some practice using that statement. Okay. And let's take a look at these two examples here next. Well, I'm going to give you an equation. It's going to be an exponential. And I want us to write the equation in logarithmic form. Okay. So all we have to do is we have to identify, what is x, what is y, what is a, and I need to write the equation then in the form y equals log base a of x. Okay, so I got kind of three examples in one here. So the first one, m equals 1.2 cubed. It looks like the x value is m, a is 1.2, okay, and the y value is 3. So now I'm just going to plug in the numbers into the form y equals log base a of x. Okay, y is 3, so 3 equals log base 1.2 is the a value of m. Okay, and go ahead and circle that. Now, when you're writing logarithms down, the inner part here, this m, that's not a power of a. Okay, so don't make it look like that. Like really shove that base down there, so it doesn't look like it's a power of a. I sometimes get that question. Okay. All right, and so that'd be my answer. Okay. How about part B? 9 equals e to the t, e meaning the number e, okay, that we talked about in the last section. So 9 is the x value, e is the base, and t is the y value. Okay, so y equals log base a of x means that t equals log base e of 9. And I go ahead and circle that. What if we had the equation 5 to the 2x equal 13? Okay, we want to write that in logarithmic form. Well, so 2x, that's the y value, right? So 2x equals log base, a is 5, and x is 13. Okay, now I'm not saying solve for x or do anything like that. All we're doing is changing one form to another form. Okay, so that'd be the answer there. Now we're going to also have to know how to convert a logarithmic form to an exponential form. Okay, so let's take a look at some of those. I got 3 examples here. We're going to write each logarithm in exponential form. Okay, so again, all I do is I need to identify, what is x, what is y, what is a, and I'm going to write it in the form x equals a to the y. Okay, so let's see. It looks like the y value is 4, a is the base, and the x value is 24. Okay, so x equals a to the y. That means that 24 equals a to the 4th power. And I go ahead and circle that. Okay. About part B. -3 equals log base e of t. E, again, meaning the number e. So what does that look like in exponential form? Well, t is the x value. Okay, so t equals e is the base and -3 is the y value. So t equals e to the -3rd power. I'd circle that. By the way, I mentioned that x can't be a negative. Also can't be 0. Okay, the input value. That does not mean y can't be a negative, or y can't be 0. Y can and will be a negative sometimes, and or 0 sometimes. In fact, with this graph, if x is any number between 0 and 1, y is a negative. You're down here. Okay, so don't. I guess the point of that is to say don't get x and y mixed up. Okay, y can and will be sometimes a negative. Okay, how about this one? So log base 3 of x plus 7 equals 5. What does that look like in exponential form? So x plus 5, that is the input. So that's going to be all alone on the exponential, equals the base is 3 and the y value is 5. Okay, so x plus 7 equals 3 to the 5th. There, now we're in exponential form, and go ahead and circle that. Again, we're not solving for x or anything. Okay. So the definition, very, very important. Put a star by that. Make sure that you know that. Okay, we're going to be using it all over the place coming up. Okay, we'll go ahead and stop the video right here in the notes, and I'll show you this example in the next video.